Sorting is a process of arranging elements in a group in a particular order. Sorting a list of elements is a very common operation. A sequential sorting algorithm may not be efficient enough when we have to sort a huge volume of data. Therefore, parallel algorithms are used in sorting. The outline of this session are the sorting problem, quicksort in the sequential manner, and the parallel versions of it. Sorting, as everyone knows, is any process of arranging items systematically. Typically, we select a key attribute from the data set as the basis of ordering. The rest of the values called satellite values in the record are permuted along with the keyword. Quicksort is a divide and conquer algorithm. It picks an element as pivot and partitions the given array around the picked pivot. There are many versions of quicksort that pick the pivot in different ways. The first element can be taken as pivot, the last element can be taken as the pivot, the median can be taken as the pivot. Based on the pivot value, the list is divided into low list and high list by positioning the pivot at the correct location. We'll see an example by sorting a set of elements using quicksort. We have to pick a pivot element. Here in this example, we are choosing 40, which is the first element as the pivot. Given a pivot, we have to partition the elements of the array such that there is one subarray which contains elements greater than or equal to pivot. Another subarray that contains element less than or equal to pivot. We are pointing to the second element of that array with a pointer called toBigIndex, and we are pointing to the last element of the array using a pointer toSmallIndex. Now we are going to compare the toBigIndex with the pivot value. Since the toBigIndex value is less than the pivot element, we are moving to the next location. Again, comparing 10 with 40. 10 is less than 40. We are moving again until we reach 80. Now, when we compare 80 with 40, the element 80 is greater than 40. So, we stop there. Now, we start again from the toSmallIndex. When you compare 100 and 40, 100 is definitely greater than 40. So, we are moving down, moving to 30. Now, when you compare with 30 and 40, you can see that 30 is less than 40. You stop there. Now, you have to swap between the toBigIndex value and toSmallIndex value. 30 will come to the position of 80 and 80 will go to the position of 30. Now, we are continuing with our loop. Now, 60 is compared with 40. 60 is greater than 40. So, you stop there. Now, we start with toSmallIndex. We are moving to 7. 7 is less than 40. So, we stop there. Now, we move to the step 3 where we swap 7 and 60. Now, we again move to 50 where toBigIndex now points to the 50. 50 is greater than 40, so you stop there. Now you start with the second step where 60 is compared with 40. 60 is definitely greater than 40, so you're moving to 50. 50 is also greater than 40. Now we are moving to 7. So when toSmallIndex is greater than toBigIndex, now we have to swap the pivot element to the position of small index. Now we are moving 40 to the position of 7 and 7 is coming to first position. So now when you see, you have divided the entire set of elements into two sets, one low list and one high list, where low list have the elements which is less than 40 and the high list is having elements greater than 40. As a result of our first recursion iteration, the pivot value is placed at the right position, dividing the set of elements into low list and high list. In the next step, we have to recursively apply the same algorithm to low list as well as to the high list. Now, after all the iterations, we have the sorted list of values. When you analyze the time complexity of sequential quicksort, it is in the order of n log n. The worst case can be order of n square. So when there is high unbalance between every elements at every partitioning step. So we can make this worst case less probable by using some sampling methods for taking the pivot value.